Good morning, my chemistry people. I hope you guys are doing awesome because I most certainly am. I want to welcome you to your second to last installment of chemistry knowledge and learning for the year. We are going to start today with organic chemistry, which is basically the study of things, molecules, whatever, that have carbon as its backbone. Now, organic chemistry is the study of the molecules that make up life. So you can dive as far and deep as your imagination could possibly go, but we are going to keep it pretty simple. We're going to start just with the basics, right? Basically carbon-based things with like a couple of sprinklings of some oxygen, maybe a nitrogen or two, and that is it. That's as far as we're going because, like I said, it can get a little bit crazy. So, after this chapter, there's only one more about nuclear chemistry, and then that's it, man. Like, we're done. So, let us not waste any more time. Let us crank into this and start learning about some carbon-based chemistry so that, we can be chemical geniuses and everything. We get smart. You know what I'm saying? All right, so here's the deal. Sorry, let me get that out of the way. Organic chemistry. We use this word organic chemistry because it is a separate field of chemistry than we have been looking at this whole year. And the reason it's weird is because it is carbon-based. Like organic chemistry is like defined as chemistry that there's a thing that has carbon. Like for the vast majority of organic molecules, like the scaffolding or the backbone of these molecules is carbon, right? So and we call it organic chemistry because when we were discovering this, we realized that it's all these molecules of living things. We weren't really sure what was going on. And it didn't make any sense that, like, my skin is made out of basically the same thing as, my blood and my bones and my hair, and that I'm made of basically the same, like, building blocks as, I don't know, that spider web up there, and the spider in it, and the bugs eating it, and Juniper, my dog over there. Like, it's crazy to think that, like, we're all basically made of the scaffolding material of carbon. All of us, every bit of us. And so, because they realized that this is all the things of living, they called it organic chemistry, and then, la-di-da, science and time happened. They realized, oh, dude, these are all carbon-based molecules. Which was like, how could everything be based off of the same element? Well, sure enough it is. Well, actually, here's why. The reason why everything can be based off of one element is right there. This one. Carbon forms, this is literally the reason why. Carbon makes 4 bonds, right? Because it has 4 valence electrons. In a tetrahedron. Now, this thing right here, this is a tetrahedron, right? It's basically a 3-triangle pyramid. It is, structurally speaking, the most stable structure you could possibly come up with, because a triangle is the most stable, and it's a triangle of triangles. It's just all triangles. It's nothing but triangles. So it's super strong and solid and steady. So it's really strong. And but here's the thing, is that it can bond with itself. That is the thing that makes carbon so very, very, very special. Now, if you look at the periodic table, right below carbon is silicone. And we can make lots of things out of silicone, like any number of things, cupcake holders, gaskets, glass. But the thing is that silicone is too big, and it can't quite make all the crazy small little intricate shapes that carbon can. Because carbon can form large stable chains, it can form rings and other forms. Man, any form you can think of can be made with a carbon, which is like crazy, but true. So let's keep on. So because there are so many like structures that carbon can make, right? I mean, it makes hair and skin, tendons, eyeballs, and these glasses. Well, like the glasses part of the glasses, not the metal part. That's a bad example. Anyway, my bow tie, my wooden bow tie, basically, man, it made out of carbon because it can make all these different things, right? We can't use regular chemical formulas. It's like it's just not gonna work. Like it just isn't, right? So the reason being is because shape and size, like the shape of a molecule is absolutely fundamentally vitally important, because shape is what determines what it is and what it does, right? Just like a key determines what it is. The fact that it's in the shape of a key means it's a key, right? If it was lumped up into the shape of a, I don't know, like a doorknob, then it'd be a doorknob, right? So the shape of something is what determines what it is and what it does. Same thing with these molecules. And so we have this thing called a structural formula, okay? And it helps us see how the carbon is put together, because if it can make chains, rings, and other like, yeah, like all of them, like all the forms we got to come up with some way to capture the shape that the molecule is making other than just a regular chemical formula. So we have, well, for us, 3 things that we're going to be looking at. The first thing that we're going to look at here is what we call molecular, and this is what you guys have been using all year, right? C2H6, C6H12, H2O, NaOH, right? So it's like element, the number of elements, element, the number of elements, and so on, which works wonderfully most of the time until you get involved with some of these larger ones. Then you're going to want this thing called a structural formula. And believe it or not, the structural formula shows the structure, right? So the molecular formula tells us that there are 2 carbons and there are 6 hydrogens, but the structural shows us the shape that these molecules, or I'm sorry, that these elements make when they form this one particular molecule. Now, this one is indeed very simple, right? However, we're starting out simple, right? Because that's how we should start. We should start simple. These can get very, very big, very, very, very complicated. Like organic molecules can get so big you can see them with your naked eye. Like, we're talking huge. So structural formula shows us the shape. Great. Last one, but not the least one, is what we call condensed structural. Now this is sort of like a mashup of both a molecular and a structural, just kind of smooshed together. You basically like name a carbon, and right after it, like, what is bonded to it? Carbon, what's bonded to it? Carbon, what's bonded to it? So in this example, we have a carbon, and there are 1, 2, 3 hydrogens attached to it. So we say H3. The next one, we write carbon, right? Because there's our first carbon. Here's our second carbon. Now there are 1, 2, 3 carbons attached to that. So we say H3. You dig what I'm saying? It sort of gives us a much better clue about what the structure is. Or we can at least work backwards to build. Like, we can go from this to this pretty gosh darn easy, and we can like build the structure and see. It's a way to condense things so that you don't have to write this big giant picture every single time you want to like write out the molecule, but it gives us a much better idea than just the molecular. Just the molecular, we have no idea what the heck is going on. So 3 ways now to draw a molecule. And for us, like these, like this molecule, we're going to start out simple. Just carbon, just hydrogen. Because the way it kind of works is carbon builds a shape, and then hydrogen kind of fills in to like plug up all the open bonds that the carbon has after it's bonded to itself, and like make all the crazy shapes. So a hydrocarbon basically has only hydrogen and carbon. That's why we call it a hydrocarbon, right? So only hydrogen and only carbon. That's what a hydrocarbon is. The end. However, of course, because it's nature and also because it's organic chemistry, there's like a lot of different variety of hydrocarbons. Man, there's so many different kinds of hydrocarbons, but we will stick with 2, the most popular, saturated and unsaturated. You may hear these a lot when you talk about, or like read the ingredients about like butters and fats and stuff. They'll talk about saturated fats and unsaturated fats, and this is basically what they're talking about. A saturated hydrocarbon has only single bonds. In other words, it is holding as many carbons or hydrogens as it can possibly like carry. So this guy has 1 here, 1 here, 1 here. There's 1 here, there's 1 here, and there's 1 here. Because remember, carbon makes 4 bonds. So it is saturated specifically with hydrogen. So just like a saturated solution holds as much solute as possible, a saturated hydrocarbon is holding as much hydrogen as it possibly can. You dig? Now, because carbon is carbon and it does weird things, we are going to have this thing called unsaturated, which is definitely different. So an unsaturated contains one or more double or triple bonds. So here's this guy. Look at this guy right here. This dude right down there, he's got a double bond, right? So if you remember, each carbon can only have 4 bonds. So this carbon right here, the first carbon, has 2 bonds already. So it can only have 1, 2 hydrogens, and this guy can only have 1, 2 hydrogens. Y'all picking up what I'm putting down there? Now these guys, man, these guys have a triple bond between them. Crazy explosive, very dangerous. I don't even like walking around with this stuff. But let's look at it. This carbon already has 3 bonds, so it can only have, you guessed it, 1 hydrogen. That guy can only have 1 hydrogen. Voila. You get what I'm saying? You dig? So let's review. We have 2 kinds of hydrocarbons. Hydrocarbon being something that has only hydrogen and carbon. We have saturated, which means it can hold as many hydrogens as possible, and it has only a single bond. Okay? So what I want you to keep in mind is that saturated has single bonds. Okay? Saturated is single. Saturated has a single bond. Saturated is single. Saturated is single. How many times am I going to say this? Saturated is single. Saturated is single. Saturated single is saturated single is saturated single. Saturated is single. Saturated is single. I'm telling you, man, I should have my own beach or something. For real. Saturated hydrocarbons have only single bonds. Now, unsaturated have either a double or a triple. At least one. It's not all doubles and triples. It's just like there's like one in there. You get what I'm saying? And so this kind of thing here leads us to this next thing called a homologous series. A homologous series. This is a group of hydrocarbons. So pretty. With similar structure and function. I'm gonna go back up there for a minute. So we have saturated and we have unsaturated. These things are these two things are different. Saturated hydrocarbons all basically behave very, very similar. Why? Because they're all the same. They all have like the same basic structure. Unsaturated, well, you have 2 kinds. You have double bond and triple bond. Double bonds, they all kind of act the same. You know why? Because they all have a double bond in there. And the triple bonds, they all act the same because they all have a triple bond. Do you guys get what I'm saying? And so this is what a homologous series is. It's a group of hydrocarbons with similar structure and therefore function. Because remember, structure, and this is important to lock down for this chapter. Structure equals function. The structure tells us what the function does, right? Just like the shape of a key. If you look at the shape of a key and it looks like the shape of the key to your house, that's your house key. Why? Because it's shaped that way. And the key to your car is shaped like the key to your car. Why is it your car key? Because the way it's shaped. You get what I'm saying? You get what I'm saying. So for us, moving around, there will be 3 homologous series that we are going to look at, and they are called the alkanes. You notice how I'm like really emphasizing the suffix alkenes and alkynes. Anes, enes, ines. Anes and enes and ines. Got it? Anes, enes, ines. We are denoting these different homologous series, or these groups, by their suffix. I hope you picked up on that. So, since there are only 3, it should be kind of easy. And sure enough, it is. So here's the thing. The general formula tells us, tells us what homologous series a hydrocarbon belongs to. Now, I want you to lock this in because we're going to look at what a general formula is in just a minute on some reference tables. But it's basically like a ratio of carbons and hydrogens. That's what the general formula is. It's the ratio. That's all it is. And so we use that ratio. Right? We're going to use this ratio of carbons and hydrogens, which is basically the general formula, to see which pattern it follows, and that is your homologous series. And so I have right down here 3 different hydrocarbons, and we are going to see what homologous series each one belongs to based on their general formula. This 3 and 8, 3 and 6, 3 and 4. So it's the relationship or the ratio between these 2 things that's going to help clue us in, right? Because they follow a pattern. Right? Everything in one homologous series follows a pattern. And you are not to memorize this. Like, the vast majority of this whole chapter, all I want you to do, learn the vocab and learn how to use the reference tables. Organic chemistry is too big. You just have to learn how to look stuff up. So here's how we do. This is how we tell what homologous series it belongs to, whether it belongs to an alkane, an alkene, or an alkyne. The first thing we need to do is count the number of carbons. Okay? You dig? And we call that N, at least for our general formula, right? See the general formula that I told you should pay attention to? Here it is. So first you count up your number of carbons. And then you look at the number of hydrogens and you compare. And for us, it's going to fall into one of three categories. You will either have 2 times the number of carbons plus 2. You'll have double the number of carbons, or you'll have double minus 2. Here's an example. For this guy, wait, let me get this here. All right, so in this case, this is 3. Okay? So that's going to be our N. So if we took 2 times 3 plus 2, let me see here, that's 6, 7, 8. That's 8. Oh, dude, I know it right there. This is an alkane. See, because it fits the pattern. Every single alkane fits that same exact pattern because they all have the same structure. So it's really, really easy to predict what group it's in, right? Let's go to the next one. Boop, 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 boop. I hate when that happens. I haven't figured out why yet. But it do. There it goes. Let's do purple. Okay. Wait, I said purple. Son. Okay, so let's check this one out. This one, we have 3 carbons again. So let's see here. 2 times 3 plus 2 is 8. That does not fit us. Okay, so again, N is the number of carbons, which in this case is 3. So 2 times 3 equals 6. Well, if we have, oh, look, do you see how that fits the alkene? This is an alkene. Super easy squeezy. Easy peasy lemon squeezy. I can't believe I messed that one up. Now let's look at the last one. Once again, 3 carbons. Now let's look at the pattern. 2 times 3 plus 2 is 6 is 8. So if we had 8 hydrogens here, we'd be an alkane. 4 is decidedly not 8. All right, 2 times 3 is 6. Do we have 6? Decidedly not 6. Okay, so this one says 2 times 3 minus 2. So 2 times 3 is 6. 6 minus 2 equals 4. Oops. Alkyne. You see how it works? You guys get what I'm saying? So once again, the way that we determine which homologous series it belongs to is first we count up the number of carbons. And then we look at the number of hydrogens, and we come here to the general formula and see what pattern it fits. You just take the number of carbons, you make that N, do a little bit of math, that's your homologous series. Dig what I'm saying? Dug. Awesome. Sweet. Moving on. Now, there are a lot of molecules in one homologous series, but you can have 50 carbons, anywhere from 1 to 50 plus more. There is really no limit. It just goes on forever and ever. For us, however, we are going to limit to 1 through 10 because why get more complicated than that? So each member in a homologous series increases by 1 carbons. In other words, we'll have methane. See, ane, so we know that we're in our alkanes. Ethane. Propane. So here's how it works. Table P is going to help us out with this. It gives us the prefix by counting the longest chain of carbons. That is missing from your notes. That should be there. By counting the longest chain of carbons. And so this prefix right here, this methane, this means you have 1 carbon, all single bonds. Eth methane, if we say ethane, this tells us there are 2 carbons. See right here, ethane, if you have 2 carbons. Methane, if you have 1 carbon. Propane, like the stuff you use in your barbecue. Propane, 3 carbons. And because it's ending in ane, all single bonds. You dig what I'm saying? So it goes meth, eth, prop, bute, pent, hex, hept, octanon, and decane. That's it. Octane. Sound familiar? Yeah, because that is the most common molecule in your gasoline, has 8 carbons. Yeah. So the only difference between propane that you put in your barbecue, it's like a vapor, and gasoline, octane that you put in your car, is this one has 3 carbons, this one has 8. That is the only difference. That's why we use it, because it's so stinking convenient. Problem is, it's killing us real slow. So we'll figure a different way. Oh, so here's this. Let's try. You thought this was no, not yet. We're gonna name these 3. So this guy, right? Here's how we name them. First thing you do is you count the number of carbons, and this one is easy. It's going to be 3. So over here, 3 is prop. So we're going to put prop. Right? And you notice I'm using the reference chart. I'm not doing this by memory. Now I've got 3,8. Remember up here, we determined that 3,8 is in the alkane. So we're going to use this suffix to tell us what homologous series it is. Propane. Propane. This prefix tells us how many carbons. And the suffix tells us what homologous series. Right? And the series tells us like how it's going to behave, whether it's just like gasoline or if it's something like crazy explosive like acetylene. Now let's do the next one. This next one is 3 carbons, so it'll be prop. Let's come right back up here to this other table, and 3,6 follows this general formula. It's an alkene, so this will be propene. Do not want this for your barbecue. It doesn't burn nicely. It goes and like kind of blows up a little bit. But prop, 3 carbons, and the ene tells us we have a double bond. Dig. Last one. Oh yeah. Prop. Now it's 4. We know it's an alkyne. Again, prefix tells us 3 carbons. And the ine tells us there is a triple bond. This is what you make like acetylene torches out of. So you don't want that for barbecuing. It's gross. Like make your hamburgers into like charcoal briquettes. Now we're done. I hope you guys have a wonderful day. I know I'm gonna have a wonderful day. I did organic chemistry. What? My day is pretty good.